Welcome, everyone. This is the, if you don't know where you are, we're at the Workshop in Entrepreneurial Finance and Innovation seminar series. We're happy to have Petra and Moser here presenting some work on women in science, lessons from the baby boom. Let me just give you a picture of the format. Let me share my screen real quick. Oh, no, never mind. I won't do that. Well, let me, because we already got screen sharing. If you look at the bottom of your screen, there is a Q&A button. I think most of us are familiar with Zoom, but just if you click on that, a little window will pop up. That's the best place to ask questions. We will occasionally answer it live by interrupting the talk. Otherwise, we will postpone it to the 10-minute discussion at the end. If you have any quick clarifying questions, feel free to use the chat to the panelists, and those will give a little more priority if there's something very confusing. So we got 40 minutes for the talk, 15 minutes for the discussion, and then the Q&A. So with that, I'll hand it off to Petra.
Thank you very much. Thanks for having me, and thanks for attending the seminar. Scott Kim, who is doing the first year of his PhD right now at Wharton, and he was an NYU student, an undergrad. And this is interesting because women continue to be severely underrepresented in science. And part of this underrepresentation might be driven by kids, by having kids. So survey data today indicate that women spend about 50% more time on kids and on chores compared with men. And when husbands are unemployed or when they earn more than their husbands. And this actually has gotten worse through COVID, and where surveys indicate again that mothers with young children have reduced much higher rate than women. And that seems to have affected scientists as well. So one thing that I think we all have to ask ourselves, what are the long run effects of these costs on participation on gender inequality? There has been a lot of research on the contribution of children to the gender gap in earnings, but we know much less about output and productivity. So there's little systematic evidence to date on that. And here's where we come in. We'll ask how children affect productivity of scientists, and specifically how they affect the timing of productivity. And then we'll look at how these differences in the timing of tenure and promotion. We'll do this at a period in time when there was an earlier shock to the cost of having kids in the baby boom, which lasted from 1946 to 64. Women at that time had children at a younger age, and they had them immediately after marriage, and the births were spaced closely together. And the other thing is that family values placed the burden of children squarely on women. So women were supposed to stay at home and take care of the kids. This is the data, not our data, but this is kind of just to remind you that there was this huge increase in fertility during the baby boom. The data that we'll use are very detailed biographies of American scientists in 1956. I'm going to show you an entry here, and I'll walk through some examples to show you what we have in data. So the source is called the American Man of Science, a biographical dictionary. It includes, despite its name, it includes both men and women, and it includes Americans in the sense of US and Canadians. It includes anybody who's a member of a scientific society. So if you are a card-carrying member of some scientific organization, then you will make it into this dictionary, and otherwise are not. Or you might be less likely. An example here is the entry for Gertrude Bell Elion. She won a Nobel Prize in physiology and medicine in 1988, and she won it because she was one of the people who developed mechanisms to develop targeted drug treatments. Before that, drugs were kind of developed by trial and error. Elion's work helped us to identify drug targets much more quickly. So it's actually super relevant to today. And the first antiviral drug that she developed was acyclovir, which is used in the treatment of herpes. And her career was kind of interesting too, because she worked at night. She was a secretary, then she checked margarine, and she got her PhD. And NYU actually told her she had to choose between getting a PhD and working. So she chose to work. And then she moved from margarine to chemistry and medicine. So what we know about her, we know her full name with the middle name, and we use that to assign gender. And we'll also use that to match Gertrude Ellion with her US patents. Then we also have her birthplace and age. And so we can put everybody into a birth cohort, so we can control for productivity across cohorts and across age. And then we also have her discipline and research topics, and that's going to be very important for controlling for variation and output across fields. Another example is Helen Wallace Toolan. She's another cancer researcher. She got her undergraduate degree in 1929 at the age of 17. She got married in 1930 at the age of 18, and she had 3 children. So we don't know when these kids are born, and so what we're assuming is that the kids were born very closely after marriage, which was the pattern of having kids during this time. She got her PhD in 1946 at age 34, that's 17 years after the undergrad. And she became an assistant professor in 1953. Another example is Giuliana Tesoro. She fled from Italy, was married in 1943, and she had 2 kids. So now I can already show you one of our data points. So Giuliana Tesoro gets married here. She's not super productive in the first 12 years, basically when her kids are probably very young. And then she becomes very productive afterwards. So I already told you that we want to control for variation in output across fields. This is really important because the propensity of a pattern varies across fields. So for example, I may not produce many patterns if I'm in mathematical analysis, but if I'm in engineering, I produce lots of patterns. So we want to control for that. And we do this by applying a very basic text analysis tool to this really nice data that we have on the research topics of the scientists. And specifically, we'll use k-means. So what we do here is we take the words that describe a scientist's discipline, here physics in this example, and their topics, and we put them in a matrix of words. In that matrix of words, the words are the columns, and each scientist is a row. So what we're going to do then, we will we apply inverse frequency weights so that we can downweight words that are not very meaningful because they are very common, like theory or research, and we upweight words that have more meaning, like neutron or polymer. And then we apply in this n-dimensional matrix, we put in k clusters, k initial data points, and then minimize the distance between the observations between the scientist and those data points, so that each scientist gets assigned to a unique field. So it works very much like a multi-dimensional OLS. And then if you kind of check this kind of assignment, it seems to make sense. So we assign, for example, we assign all of these terms: aeronautical engineering, aeronautics physics, mechanical engineering, flight, research, stability, and guided, to a field that's called aircraft. And so now we can, what that allows us to do is it allows us to assign each scientist to a field. Why is this important? Well, it's important because two scientists could be in different disciplines like engineering and physics, like these, like Cesar Fragola and Elder de Turk, and they could still work on very related research topics. So they both worked on aircraft, for example, and the k-means allows us to capture that, whereas a simple analysis based on disciplines would not have done that. Then the next challenge is we need to assign, we need to figure out who was a woman in the data. That actually is much harder than it looks. We tried 4 different ways, comparing each of them to people who actually worked at who studied at women's colleges. We're assuming that they're women. And then, so what we're using the US Social Security Administration data on first names. So using that data, we assign people to a gender based on their first name. And then we match the data with patents and publications. So now we match scientists with patents and publications. And so for the patent data, it's really important that we have a very high quality match. So what we do, we use the age of the patentee to filter out false positives. So let me just show you how we do that really quickly. So the first thing we do, we match on the middle names. So this is the data not matched on middle names, and these are the data matched on middle names. So what you see is that we get a lot more noise when we're not matching on middle names. And then the focus of the pattern analysis is going to be on STEM, on the physical sciences, chemistry, physics, engineering, and math. And when you look at the other fields, patents are not a fantastic measure of innovation in those. So in the physical science, on the biological sciences, physical sciences, you get a nice distribution of age. Biological sciences and social sciences is not so good. And then the other thing we do as a final step, we drop all names, we exclude all names that are super common. So if your name is John Smith, I can't do anything to really reliably match you to patent data. And so let me just show you why all of this is super important. So if we just start with a very naive matching, like a Levenstein matching, where we match scientists to their names with patents, just using their names, we get a false positive error rate. So patents that are assigned to people when they're like 5 years old, for example, or 140 years, of 83%. So 83% of the matches that are just based on the names alone are false positives, are completely in a nonsensical error in an age range. So we can cut that down significantly through that process I just illustrated. We can get it down to about less than 5%. We get it down to 4.2%. So we think we have actually pretty good patent data. We have good patent data for our scientists. And then the next thing we do, we match them to publications. And for that, we use Microsoft Academic Graph. We're matching the scientists with the author ID, and we focus on journal publications. And here, the benefit of this is that we can actually do this for all disciplines. So now we can look at STEM, and we also trust our data more for the biological and the social sciences. Let me give you an example of that one too. So here is Gertrude Elion, for example. She was super productive, even though she didn't have a PhD. And so she had 105 publications. And we're going to focus here on journal publications. So she had 75 journal publications. Overall, we have 750,000 journal publications by 46,000 scientists. So that means 2/3 of our scientists have at least one publication. And then this is, I think, is kind of hilarious. If you know who College Razi is, like I'm showing you a paper on the baby boom, and the guy with the largest number of publications is the man who invented the birth control pill. So that's, and then we have Jane Marion Oppenheimer as the woman with the largest number of citations. So now let me show you some results. So what we're interested in, we want to see productivity differences across demographic groups, but across the life cycle. So I'll first just show you raw data. And so what the raw data suggests is that mothers reach peak productivity at a later age than fathers. So mothers reach peak productivity at age 42. So there's a lot of noise in this data. I'll show you not many of these mothers actually survived in science, but then I think there's a clear upward trend, whereas fathers have sort of a more typical pattern of productivity, and their productivity peaks around age 30, 35, and they're sort of productive until 40 and then kind of gradually decline. Mothers are also more productive relative to other women. So we think that's actually selection. We talk about this more later. So mothers just peak later. So they peak in their late 30s and early 40s. And then what's really, I think, interesting is that when you look at compare the productivity patterns across the life cycle for men and women without kids, there's really no difference. So they actually seem to be productive at roughly the same time. So now we're going to look at this more systematically. And what we'll do, we'll estimate OLS regression separately for the demographic groups. So what we're doing here is we're comparing mothers with themselves when they're younger, where age 20 is the excluded group. Why are we doing this? Well, we're doing this because there could be actually differences across. They say there might be, if there's discrimination against women, then mothers may just pattern less overall. So we want to compare for these tests, we want to compare them with themselves. And then we're controlling for year fixed effects because there could be changes in output over time. For example, there want to be changes in output with variation in funding. And there could also be variation in productivity across cohorts. For example, if women of a certain cohort are more likely to have opportunities in science because they come of age in a period when there is a lot of demand for female labor. And then I already explained why we need the field fixed effects. So we'll have those also in the regressions, and we take them out in robustness checks. And so when you look at this overall data, again, the dominant fact here is again that this peak in productivity for men, but then you see that mothers' productivity, mothers' patenting productivity, and the productivity of other women looks very different. And again, you see that the productivity of mothers does not follow this peak around age 35. Instead, it continues to go up until the early 40s, and it's relatively high until the 40s and then goes down. So now I'll just look at differences in inventive output across demographic groups. The first thing you see is that mothers tend to produce more patents than other women, but they are much less productive than fathers. And that could be even at this time that actually, if a woman was working on a patent, she may actually not have gotten her name on a patent. So there are many different factors that could play into this difference. It's not really the focus of our paper, but it has been established in lots of other papers. So there's some evidence that actually there's even still discrimination at the patent office today. Petra, and then we also confirm that fathers are more productive than other men. That's also something that other people have found before, not for productivity, but for earnings. So typically they just show that fathers earn more. We actually show, yeah, actually maybe they deserve some of it because they also produce more stuff. And then we're going to just rerun this now as a simple OLS, just so that we can see whether the results are robust when we throw in controls. So what we see is that women patent 67% less compared with men. That's its coefficient of minus 5.8 relative to the pre-baby boom mean of 8.8. Mothers patent 77% less compared with fathers. And then also mothers patent 9% more than other women. So that actually can be due to selection, if only exceptionally productive mothers survive in science. I think that's one of the first indicators that there could be selection. That's robust to controlling for the age of the scientists. So I told you we have the cohort fixed effects and we have year fixed effects, but instead we can put in age fixed effects. The results are very robust. And in the main specification, we restrict the analysis to scientists up to age 65 because then many of them retire. We can do this up to age 80, doesn't really change anything. I think what's more interesting is that the gender the difference in other disciplines is worse than the biological or the social sciences, because when we pool our data and we put in the biological and the social science, it becomes smaller. So women patent 52% less, 67% if we just look at STEM. But the estimates for parenting are nearly identical. So even though we see across disciplines, parenting seems to have the same effect in STEM and in the biological and the social sciences. Now, again, let's take that with a grain of salt, because this data on the biological and the social sciences is patent data. And so I'll show you the same results later again with the be a little bit concerned. Now, let me show you one other thing in case you're wondering whether you should have more kids. Highly on your gender. If you are a woman, like, actually, yes, you should. If you already have one, go ahead. So the first child carries the largest productivity penalty for women. And men, and I think this is purely against selection, for men, productivity increases with each child. So men who have more kids tend to be more productive. And that again could just be selection to parenting, right? You have more money, you can have more kids. Or it could be that, say, if there's very strong gender differences and you have like a really strong, smart woman at home who's like watching your kids now, she might push you to work a little harder. So we don't really know. Agnostic on that. But now what we're interested in is like what actually happens to the productivity of scientists after. And so to do this, we want to understand how children impact scientific output. The ideal experiment, of course, would assign fertility at random. Now we can't do that. So, but we can estimate an event study, because say there might be things that make me less productive. Maybe I have a preference for woodworking or for leisure over research. But however that would affect my productivity over time, that should continue fairly smoothly. Like if I'm a slacker, that is going to affect my productivity fairly smoothly. Whereas the event of marriage and then having a kid afterwards creates a very sharp change in my productivity. So again, that's what we'll exploit. And then the other really nice thing about this event study is that it allows us to exploit this long run nature of our data. Because I think one thing that we have that other people did not have so far, so we have like a long career history for these people. So now how we're going to estimate is the structure is very similar. Now we'll have an event study where the outcome variable are patents by the scientist I in demographic group D. We'll again have year fixed effects, we have age fixed effects, field fixed effects, and the excluded period is the year just before marriage. And again, we're comparing people to themselves before marriage. And just to give you a rough idea, the median age of marriage here was 27. So what we see here is that, again, for men, for fathers, we find the same productivity profile, so that they become more productive for about the first 10 years of their marriage, and then they become less productive afterwards. Other women just become less productive. That can actually be because women just in this period specifically had to move with their husbands all the time. And so that actually, with each of your husband's move, that kind of reduces the quality of your job match. And but then what you see for mothers, actually, when you have a kid, mothers, again, they are less productive for the first 15 years, but their productivity really picks up 15 years into the marriage. Now, 15 years into the marriage, that's when the kids are actually kind of not that much work anymore. So this is from the American Time Use Survey. And so basically when kids are really young, this like your life's miserable. They're not miserable, but busy. And then the kids become more independent over time and they kind of become less work. And so I think by age 12, you can kind of let them go. Right? So they're not that. So I think that's actually, so my interpretation is that this is actually happens at a time, this change happens at a time when actually kids are less work. Other people have suggested that this could be pent up research potential. I don't like that explanation quite as much. I mean, I find it very hard to imagine that women think about research while they're changing diapers, but maybe, but like you don't even have to go to that image. You can just actually think about very general job models. And so basically, if you don't work, your skills become obsolete and your productivity declines. So I think that's probably not such a great explanation. So now let's actually see how that, how these changes in productivity over time affect publications and tenure. And so because it's not called patent or perish, it's called publish or perish. So we want to use the publication data here. Again, so what we're going to do the same analysis, but now we're going to do it with publications as an outcome variable. And so the first thing I'll show you is that the publications actually have a different time pattern. So it actually for publications, which I think is interesting, but maybe not for this paper, but I think it is still very interesting that for publications, actually the age distribution actually looks more similar for men and women, right? For patents, essentially, it was like it's pretty flat and then productivity increased. I think that is because industry is probably not a very good place for a woman to be an academic scientist at this time. Claudia Golan has written a lot on this. Basically, if you have to go to a lab, that's very difficult to do if you have small kids at home. Whereas maybe academia offers more flexibility, so it's actually not such a bad job. So that maybe gives us a kind of a more equal distribution for men and women. But even in that, you see that mothers and only mothers have this dip in their productivity after age 30. So they get, the median age of marriage is 27 for all scientists, for men and female scientists. And then women are less productive in that time. And then they actually, after age 35, they kind of recover and their productivity increases. So it's the exact same pattern, right? I show you different data, and yet it's the exact same pattern. So it's the women, mothers become more productive after age 35, and it only holds for mothers. Now, one thing that, again, people might say is like, well, but maybe they just had these ideas that they were sitting on, and then the ideas that they publish later on are garbage because they just sat on them for a longer time. Not so at all. So we just started getting the citation data. So this is the very first graph that we were able to do like this past weekend. And so I just wanted to show you that. So they're not that significant differences in the quality. So these are citations per publication. And so first of all, one thing you see is that publications by mothers actually are on average higher quality. Like you compare publications by mothers and you compare them with publications by fathers, they're higher quality. And then actually the other thing that you see is that the publications by mothers, actually they increased relative to the other scientists, again, after age 35. So that's where they actually put some quality differences here. So then again, let me just estimate these differences across demographic groups just to kind of get like, I think mostly to connect our findings to those in literature. And so what we find here is that women publish 73% less compared with men. That's very similar to the patenting results. Mothers publish less 83% less compared with fathers. But interestingly, again here, mothers publish roughly the same as other women. So why is that? I think that's probably the most interesting part of that comparison. So again, let me remind you that mothers in STEM publish roughly the same as other women, but they publish slightly more, but they patent slightly more than other women. So that could be, again, because of selection. So mothers may be less able to do the long work. So the ones that survive are super, super productive. And so that could just be that they are more productive than other women because they're exceptionally selected. On the other hand, it could be that motherhood reduces the publishing productivity of mothers in academia more than in science. For example, it could be that mothers are less likely to get tenure. And then when you are less likely to get tenure, obviously you get worse resources. And so that reduces your publication productivity. And so we're going to examine both of these channels below. Then the other interesting thing is that we can confirm that gender differences in other disciplines are smaller than in STEM. So again, when we expand the data to all fields, including the biological and the social sciences, the coefficient gets a little bit more negative, but it's actually relative to much higher mean number of publications. So actually women publish 62% less compared with 73% less in STEM. So we see the same result, that gender differences, again, matter less in other fields compared with STEM.
Petra, you have 10 minutes.
Okay. So now let's look how this affects tenure. And so I think probably the saddest result is that mothers are much less likely to be promoted to tenure. 27% of mothers are promoted to tenure. That's 19% less than women without kids and 21% less than fathers. But one interesting thing here is I think that having a kid is like the main driver of not getting tenure. It's not so much gender, it's actually just having a kid that hurts you. You can also see this, we can see how long it takes you to get tenure. And so what you see is that mothers are as likely to get tenure within the first 5 years, and then mothers kind of drop off, fall behind, and the rest of the population, the other demographic groups, keep going. So now let me show you event study estimates for tenure after marriage. So how does actually being married, how does it affect your probability of holding a tenured job? And so here, again, I think, so for men, probability of tenure after marriage goes up. For other married women, it stays roughly constant. And for mothers, it declines. So actually what this shows is that they actually, not only are they less likely to get tenure, but they're also more likely to drop out of having a tenure job. So even once they have a tenure job, they're more likely to leave academia. So this shows actually women actually even leave tenure jobs. Mothers leave tenure jobs, sorry. So now actually let's look at changes in publications before and after tenure. So first I want to see is like whether women who do not get tenure, what happens to them, whether that actually affects their productivity. And so mothers who do not get tenure, they actually have the same productivity profile. So they fall behind, but they continue to be very productive until their mid-50s, long after others have started to decline. But mothers who do achieve tenure, they're actually very productive in their late 40s. So mothers who actually achieve tenure, they fall behind here. So the rate of change declines. And this is interesting because it's actually, again, it's the age of marriage. It's the median age of marriage. That's when their productivity drops. It continues at a lower level and it rises slowly at a lower level than other men, but it rises until their mid-40s. So now without actually, there's no causality whatsoever here, right? So I'm not saying because in an ideal world, publications would actually determine tenure. So I want to just look at what happens to productivity of different demographic groups after they get tenure. And so ideally, if you think about this, we use tenure, we give tenure based on our prediction of future productivity. So ideally, we should see no differences here. But that's of course not what we see. So what we see for men is that productivity increases until tenure, and then kind of it stays flat. For other women, productivity goes down. That could be because, but it's not super strong, but it declines. Could be because, again, they have to move with their spouses after tenure. But for mothers, productivity actually really goes up after tenure. And I think if that, obviously this is not causal, but I think what this at least tells us that we're very, very bad at predicting the probability, the future productivity of mothers. So I think we're really undervaluing their productivity. So now let's look at selection and whatever time I have. So I'll just tell you, we'll look at selection at there's a lot of selection in this data set. So first we're going to look at selection to a PhD. Getting a PhD was really hard at this time because some programs still would not allow women, and others would actually just say, like, look, you're a woman, you're going to get a PhD, and then you'll have kids. What good is that going to do? And so they would actually not take women students. So that would all mean that women should be less likely to have a PhD. That's actually not the case. Women are more likely to have a PhD. And that, I think, tells us that women had to be more qualified to get the same jobs. Interestingly, there's no difference in how quickly they move from undergrad to PhD, with or without kids. But mothers already get pushed out or drop out from the first stage. They're likely to get tenure track jobs. 36% of mothers become assistant professors, compared with 45% of fathers and 45% of other women. So when you have a kid, you're less likely to get an assistant professor job. They're also slower to get there. So mothers take 4.4 years to get the first tenure track job, compared with 1.3 years for fathers and 2.8 for other women. So then mothers internalize this, or women internalize this. So they basically say getting married is super costly. Now, not so much. I will not do this. So female scientists were less than half as likely to get married. 40% of female scientists married, compared with 80% of men. And so you see that it actually improves over time. This is, again, consistent with the work of Claudia Golden. Like the early cohorts, they were like, no way, you can either have a job or a husband, but you cannot have both. So here, over time, this improves and then it kind of flattens, but these people might be too young to get married. Women also marry later than men. Female scientists marry later than men. So the median age of marriage for both of them is 27 years, but if you compare it to the population, men in the population, and even college-educated men, marry at an older age, whereas women marry at a younger age. Then 22% of female scientists had kids, compared with 74% of men. And that, again, improves a little bit over time, but then actually for this generation really drops down. Once they have kids, again, this is very consistent, right? We said before, like, it doesn't matter how many kids you have, you're kind of already, you're So once you have kids, there's actually not that much of a difference between the number of kids that people have. So again, not the purpose of our paper, but it seems like it's the first kid that really matters. And some people have said, okay, there is underrepresentation in science because women have a preference for like softer fields. I just tell you that's garbage. So we can match them really well. True, actually, women are overrepresented in these super hard fields. And I think, personally, I think that's because you can't afford to discriminate if you need somebody who's like has a very, very specific skill. And
one minute, Petra, 1 minute.
Okay, so women are more likely to drop out if we compare them with women are twice as likely to drop out of science. We compare the university directories with the men of science. And then I wanted to show you just one thing that kind of motivated me to even write this paper. So we were checking checking the data for like inconsistency. I noticed that there was, so this is actually truncation, right? So these people could just be too young to make it in the men of science. They're not like, they're not prominent enough, or they're not yet members of scientific organizations. But what is really striking is that the drop-off for women happens actually here. And these are the women who are of childbearing age at the baby boom. We can also look at this when we look at entry into science. So we know when they entered science. This is the run-up in World War World War II, sorry. And then there's a big decline. But what we see again here is that this decline in entry into science is driven primarily by women who were of childbearing age. And so we think that that's sort of a lost generation of mothers of the baby boom. And I'll stop here. Thank you.
Okay, so thank you, Michael and David and Song, for inviting me to discuss this incredibly interesting and incredibly depressing paper. Very much enjoyed sort of reading it, and I like to start my discussion with an anecdote. So here is someone that in some sense should have been in the MOS directory, but you know, in sort of separate conversations with Petra, apparently wasn't. So this is Beatrix Ann Hamburg. She was a pioneer in the field of adolescent psychiatry, eventually very prominent foundation president and so on. She's smack dab in the demographics that Petra is interested in. You know, men and women of childbearing age at the time of the baby boom. She got married in 51 to another academic, 2 children born in 53 and 55. And here is the thing that I find really interesting about her career. She when at the time where we might have thought were the years of sort of peak productivity, she was sort of a trailing spouse at Stanford, and for 10 years she was in this sort of research associate position, so not on a tenure track, joining the tenure track only in 1976. And I think that's sort of like not uncommon for, you might say, female survivors in academia during this period. And so even though she is not in the directory, and we'll get back to this, I think it's sort of, you know, the structure of her career is actually quite consistent with the findings that Petra reported today. So, so this is a paper that, in my mind, is building a very strong circumstantial case for the, I shouldn't say the existence, the existence of lost Marie Curies, or the absence of Marie Curies, in this particular sort of demographic slice and time period in US data. Okay, so the really novel data source here is this American Men of Science directory, the 1956 edition, and that gives Petra 80,000 plus scientists in academia and industry. And just to be clear, and I'll get back to this, roughly 80% of those academics are actually in academia. Okay, so gender is imputed, but I feel like that's not too much of a big deal. I think you can do very well by imputation of gender today. You know, with many more scientists with Asian names and Asian first names, it's much harder to do today than it was to do that in the period that Petra studies. Okay, it's matched with US patent data, and there's a lot of work that went into this. And then the surprise bonus for today, which was not in the paper, is that Petra actually matched it with publications, and with MAG specifically, which I think is exactly the right data source for this. So she sort of like cut off my legs, you know, like the discussion, like is all like, anyway, I'm gonna have to recover because a lot of what I had to say was about publications versus patents, but I'll try. So she and Scott document these patterns of correlations that speak to a very large motherhood penalty for female scientists. So just sort of, so the mother's patent output peaks much later than men and other women. There's this even study evidence, which is in some sense like a pretty good smoking gun, I think, that points to depressed output in the first 15 years post-marriage, then followed by a pretty steep recovery. We have cohort level evidence that points to decline in the entry of women of childbearing age. And then finally, we have tenure rates and speed of promotion that are much lower for mothers, both relative to men and other women. So overall, I think, a set of results that really, like, I thought it was very it was very interesting, but also very depressing, because there are women that were missing, there are innovators that were missing, and there might be innovations that were missing as a result. Selection. And Petra was a little bit rushed at the end to talk about selection. I have to say that the selection aspect in the paper that interests me the most, and I would like to see a lot more on, is selection in getting a listing in the directory. Okay, so like trying to understand exactly how entries solicited. And there is actually some evidence in the paper, which I think is super cool, which is that Petra digitized university catalogs, sort of directories for, I think, Columbia University, and maybe the UC system is in process. And so you can look at all the people who began a career and then the extent to which they actually show up in the directory in 1956. And I think that should get more play. I'm hoping that you'll be able to do more on this, because I think that in some sense, if you think about the data in this paper, it's true, you have this very long time series for the output, right? But in terms of the individuals themselves, it's a single cross-section in 1956. So being able to sort of see them at entry and then see if they end up in a directory, that's in itself a very, very interesting outcome. And you said it very briefly, right? But in this very small sample that you've analyzed, men appear twice as likely to get a listing than women conditional on entering academia. Okay, and so I think that this extensive margin story, right, is incredibly important. And in some sense, the paper is focused on the analysis is all about those women who made it to be in a directory, right? So they're by definition very selected. So you should be double depressed about the findings in this paper, right? Because those are, to show up in the directory, they're already extraordinary, probably. Okay, so I was a little bit frustrated about the focus on patents when I was reading the version of the paper that was sent to me. And then, surprise, and really good surprise, Petra added publications, right? So here is the thing. Patenting output is, I think, a lot better window on the productivity of industrial scientists relative to academic scientists, certainly in this era. We're talking about pre-Bayh-Dole, okay? Academic patenting was simply not a thing. I'm not saying it didn't happen, but it happened sort of very, very rarely, right? Whereas publications, obviously, that was what you were supposed to do as an academic. So much of the rhetoric and examples in the paper are actually motivated by academia. Much of the data is from academia. So I think, so now it's great. Now you have, in some sense, the best of both worlds. And I think that it would make sense to run some analysis on academic scientists on publications alone and industrial scientists on patents alone, right? But I think a reasonable conjecture, so the question is, how do we think about the choice? There's selection between industry and academia that maybe you could think about as well in a little bit, right? So in general, I tend to think that the tenure system actually amplifies the motherhood penalty, right? Because it puts women in this sort of time crush in the years of peak fertility. And so my naive view would be that women and mothers would preferentially select into industrial careers where sort of like maybe industry can live with sort of a slightly smoother productivity, like, productivity profile. But we actually observe the reverse in the MOS data. And so this could be for the reasons that Petra mentioned, or it could be about something about the way in which MOS solicits listings for women and men, and how far they searched in industry versus academia. And one possibility is that they're quite exhaustive in academia and not so exhaustive in industry. How long do I have, Michael?
I think you have about 6 minutes.
Oh my, okay. Well, that's going to leave more time for the discussion.
Oh wait, maybe 5. Five.
I talked too quickly. So some things about the data that I think would be worth thinking about, right? So parent status here is inferred from explicit mention of kids in the profile, right? And the question is, if you don't find mention of kids, does that mean they don't have kids? And I'd like to be more sure of this. And I've had this, I've encountered this, like the who's who looks suspiciously like the MOS directory in the way in which it's structured. So I've used the who's who a lot for my superstars of medicine papers. And there are, it's pretty clear that there are, in some sense, there are profiles of scientists in the who's who that are sort of all business, no personal information. And others that have the full gamut of things that you're being asked to report, including, family information, marriage, number of kids, and so on. So I think that Petra is in the process of matching this data with maybe 1940, 1950 censi. I think if you could sort of cross-check whether the absence of evidence is the same as the evidence of absence, as far as kids are concerned, that would be important. I would also like to see some crude Becker-style tests, right? So I'd like to know how productive did women or mothers need to be to get tenure in your data, conditional on being in academia, but also to be listed at all, like using your directory information. I think that would be very informative. And would speak a little bit more directly on the selection into the directory itself. And as well, let me end on this. I think that, coding the careers of like thousands of scientists sort of in the same era for my own research, I encountered numerous cases. So those are anecdotes. Beatrix Hamburg is a good example of that, but there are many others of women who actually exhibited very high productivity, were in academia, but in these sort of marginal positions. Research associate, like not the tenure track. And I think that's information that you actually have, and I think you could play it up a little bit more. The likelihood of being in a stable versus a marginal position. Because it's very, very striking that if you're looking at sort of like, in some sense, what you might call the date of independence for a female academic in this era, it tended to be often very, very late in the career, like 20 years post-PhD or post-MD, which is crazy, right? And so I think the way in which the motherhood penalty might have played out is in this particular way, and I think you have the data to document it carefully. So I think you should do that. Let me stop here. Just said this is like, like the stuff that you've been adding without telling me is in the process of making the paper even better.
Great. Thanks, Pierre. And I'll just take the blame. Maybe I sent an old version as we saw it discussing. So I'll take all the blame for that. Petra, do you want? Yeah.
Like in the last 10 days. Oh yeah.
Okay, so if you want to, do you want any time to respond to Pierre? Otherwise, I can open the floor.
Thanks. So I want, so this is obviously all great. So thank you very much.